So again, this last section is called harmonic motion, and there's two types of harmonic motion we'll discuss. We're really only doing problems with simple harmonic motion, so the simpler ones, versus dampened oscillatory motion, which I'll explain at the end. But basically what we're saying is that if you have a spring that is at rest, option A right here is like the weight has been balanced, it's not bouncing up and down at all. And if you were to pull that spring down to level B right here and then let go, what happens with a spring? It bounces up and down and up and down and up and down and up and down. Now, in real world for physics, there is friction that would keep that spring from going on and on from negative infinity to infinity, but mathematically we can forget friction for a little bit. And if friction is forgotten, or neglected, negated, oscillatory motion, the bouncing back and forth motion, is described mathematically by a sinusoid. That's sine and cosine. So what we're saying here is that these oscillatory or back and forth motions can all be modeled by a sine or a cosine function. This would include springs, it would include sound waves, electrical currents, and electromagnetic waves. All of these ideas of things that bounce back and forth between two maximum and minimum values can be recognized and written as a sinusoidal function. The position of a point oscillating, going back and forth, about an equilibrium position, that's like your midline, at time t is modeled by either a times cosine of omega t or a times sine of omega t. And let's break down what each of those things might mean. So if we are using the cosine function, because we know what the shape of the regular cosine function looks like, cosine starts at a maximum value, correct? And then it goes down and then back up. So that means for cosine, we are starting this function at either the maximum or the minimum. For sine, since we know sine starts at the midline on the y-axis at time t, time 0, we know that this is going to be the ones that we use when we start at the equilibrium or at the midline. We would choose to write a sine function as opposed to a cosine function. Now, if you took AP Pre-Cal last year, you know that FRQ 3 was all about writing one of these sinusoidal functions, but you had to pick 4 letters. You had to pick the A, the B, the C, and the D. In our textbook, we're only working with changing the amplitude and changing the period. We're not changing the phase shift and we're not changing the midline due to the examples that we're going to use. But I know, based on what we've talked about with functions, that this number in front of the sine and the cosine does change the amplitude of the function. So we know, based on what we talked about in previous classes, that the amplitude of our motion would be the absolute value of A. It would tell us how high that spring goes up before it comes back down, or how low it goes until it comes back up. We also know, based on what we learned about omega when we did the section in chapter 3, we know that the omega kind of tells us how many times that this is happening. It is the angular velocity. So it helps us find out that the period of the function is going to be 2 pi divided by that omega. Since the omega is sitting in the function exactly where B was in our previous chapter for transformations, we now can give it an application of omega, which is your angular velocity, angular speed, which is kind of cool. And so our whole job today is to be able to take a scenario that is presented to you and figure out the amplitude, figure out the omega, the B value, if you will, so that we can find the period of the function, or taking the period and finding the omega, so that we can write these equations and then use them. As a quick aside, just because I know somebody's going to ask me this question and I want to get ahead of it, if I was given the period and I wanted to find omega, I could find omega by doing 2 pi divided by the period. That's just resolving this first equation for omega, which just means we can work either way. If I want the period given omega, we use the first one. If I want omega given the period, I use the second one. So it's just solved the other way. Let's see what an example might look like. We're going to go back to that idea of a coiled spring. Suppose that an object is attached to a coiled spring. It is pulled down a distance of 5 inches from its equilibrium and then released. The time for one complete oscillation is 4 seconds. So for me, I like to draw a picture because I'm a visual thinker, which means here's the spring. I'm just pretending like that string is a spring. And this is my equilibrium point. But to start this motion, I pull that spring down 5 inches before letting go. And once I let go, it's going to start from this lower starting point, and it's going to go up and down and up and down and up and down, making that sinusoidal wave based on the different distance from the equilibrium point. I was also told in this problem that the time for one complete oscillation is 4 seconds. When they tell me one complete oscillation, what have they told me? For a complete oscillation, what is that called? Okay, normally 2 pi, because 2 pi is the what? The period. So the period of this scenario, the time it takes for that spring to go from the very bottom all the way up and back down again is 4 seconds. Okay, those are all the things that we know. It says, give an equation that models the position of the object at time t. Well, to write that, we first need to choose if we're writing a cosine or a sine function. Why sine? Does it? Don't I pull it down first? Which means it's below the equilibrium point, yes? This is the equilibrium point. Once I let go from here, the spring is going to go back up above the equilibrium point and then back down. And assuming there's no friction, it will reach the same height, max and min, the entire time. Does that make sense? So it means we're not using sine, we're in fact using cosine. To write a cosine function, all we need is an a value and an omega value. Let's think about a for a second. Since this is our amplitude, how far did we stretch the spring down before letting go? How far did we move it from the midline? 5 inches. And we moved it in the downward direction, correct? So it's like I'm flipping over that cosine function. My amplitude here, well, my amplitude is 5, but my a value is going to be -5 because it's like we pulled it down, my reflection over the x-axis. And now we need omega. What did they give us that will help us find omega? The period. We know that omega is 2 pi divided by the period, so to find omega, all I have to do is go 2 pi divided by that period. So it's 2 pi over 4. 2 pi over 4 reduces to pi over 2. If you have a and you have omega and you've chosen between sine and cosine correctly, you can write the equation. The position at time t is going to be -5 times the cosine of pi over 2 times t. We plugged into this equation, sorry, wrong one. This equation, the a value of -5, distance of 5 downwards, and the omega value that we found based on the period. Does that make sense? Some further questions I can ask you once you have the simple harmonic motion equation written is something like part B that says to determine the position at time 1.5 seconds. My friends, if they gave you a time, what can you do with this number to find the position? Plug it in. All I'm asking you to do here is take 1.5 and plug it into the S function, which means we're calculating -5 times the cosine of pi over 2 times 1.5. Now this will definitely be a question we're doing in our calculator. Some of us might be able to have done this in our head. But we're going to go to our calculator. Now, our calculator should be in what mode? If we're using 2 pi's. Radians. So since our omega is always in terms of radians, when you're calculating some simple harmonic motions, we do need to change our calculator into radian mode. Easiest way to do that is just reset it. Second plus 712, it resets into radian mode. If you trust me to type this in correctly, / you shouldn't trust me because we've seen me mess up many a times, we should get approximately 3.54 inches, which means it's 3.54 inches above the midline, 1.5 seconds after releasing. So it's already gone up a little bit. The last question here says to find the frequency, and I'm going to add a little caveat here that we're finding this frequency in oscillations or rotations per second. So we're going to find the frequency. Now the frequency has everything to do back at the period of the function. When we wrote down our period, we said that we were going to have one oscillation per 4 seconds. But I want to know how many oscillations in 1 second. So if I were to take 4 seconds and put it into 1 second, it's like I divided 4 by 1, correct? So if I take 1 and divide it by 4, that means that we're going to have a fourth of the oscillations every 1 second. So my frequency is 1/4 of an oscillation per second. The second type of harmonic motion we're going to talk about today, and we're really just talking about it, there's not an example here, is called damped oscillatory motion. So this is kind of what would happen like in more real life. So if we think about that spring, and in real life, if we let it go, it would bounce up and down, but would it keep going for forever? No, the oscillation would get thinner and thinner and smaller until it goes back to rest. So it has been dampened, if you will. That's the word that's used for that. Here's that word spelled out so that you're not just like, what is she saying? It has been damped or dampened by the force of friction. Most oscillatory motions are damped. For example, shock absorbers on a car stop you from hitting a pothole and bouncing for the rest of your life. They dampen the weight of the oscillation, getting you back to equilibrium. So a decrease in amplitude of a damped oscillatory motion usually follows the pattern of exponential decay, meaning it's bounded by 2 exponential decay functions, one that is reflected and one that is normal. So if we look at this is an example. Let me point with the pointer. This is an example of a oscillatory motion. So there's the cosine of 2 pi times t, right? But the amplitude has this exponential function in it instead of just a regular number. So what that means is the function is going to start off with the amplitude of 1, but then eventually the amplitude is going to thin out until we reach back to equilibrium. It's like it is bounded by that exponential function on the top and the reflection of it on the bottom. So instead of bouncing back and forth to the same minimum and maximum every time, it's bouncing back and forth to the minimum and maximum, air quote, of those 2 other functions, which I think is really cool because it's 2 different types of functions we have learned about either in college algebra or this class put together into one. You won't necessarily see at a lot of example problems at all from me in regards to damped oscillatory motion because we're going to stick with the simple harmonic motion, but I still think it's cool and worth talking about.